Hello, my name is Matthew Newland. In this video, we are going to be deriving two functions. Both of them are going to be dealing with a particular altitude. One of the functions is going to be pressure, and another function is going to be temperature. So there's a couple of assumptions we need to make here, at least for this particular scenario. We are going to assume that the temperature decreasing as a pocket of air rises and expands is a completely adiabatic and reversible process. So what does that mean? So we're going to start here just with a simple picture to start off first. So our first picture, so I'm going to move this chair out of the way. So our picture is going to look something like this. Our picture is going to have just a pocket of air. This is our normal pocket of air, and it's going to expand up to here. And we're just going to say that this position is 0, and this new position is at a height of z, or an altitude of z. So what does it mean that we have an adiabatic and reversible process? So we'll say reversible first. A reversible process is just a good way of saying that the pressure inside the sphere and outside the pocket are equal to each other. And what we mean by adiabatic is that an adiabatic process is saying that there is no internal heat in the system. And we also are going to assume that this is an ideal gas, so we'll just write down our constants for our equation for an ideal gas to find either pressure, volume, or temperature. So we have our pressure, we have our volume, which is going to be equal to the moles of gas times our gas constant times temperature. So with these sort of properties that we have labeled this sort of scenario right now, what can we do in order to find out a function that can tell us how our pressure and our temperature is going to change due to this particular altitude? So we're trying to start, well, in the problem question, we need to start with our basic equation of fluid statics. So what is that? Our basic equation of fluid statics, we're going to come over here and write it out for you. Basic equation of fluid statics. So our basic equation of fluid statics goes as such. It's going to be that the change in pressure is a ratio to the change in our altitude, which is going to be equal to a density times acceleration. And because this is not, in another way we can put this is, at least in this form of, at least in this scenario, is that density, or negative density, due to gravity, or density times gravity. And that's negative because we're trying to say that our z value, is in the positive y direction, and that our gravity is in the negative y direction, going down. So our gravity would be as such. So these are just our basic properties that we're going to start working with now to find our functions now. So what can we do with all of our properties that we have labeled in our ideal gas equation to start trying to solve something? Well, we got to start somewhere. So let's start with trying to get rid of this density. We're trying to find an expression that's going to be able to replace this density value in this far right equation here, our negative density times gravity. So let's just write out our idle gas over here. So we have pressure times volume equals moles of gas times gas constant times temperature. So with these properties, what do you think we can start working with here? And let's write down what our density equation is going to be, because that also has an expression. Density is going to be equal to the mass of an object divided by its volume. That's the normal density expression that we can use. And if you notice, we have two things in here that we can kind of manipulate around here. We have volume, which you can see is in our ideal gas equation. So we can immediately say that this expression can be kind of manipulated around to have a new expression where our volume is actually equal to the moles of gas times our gas constant times temperature over our pressure value. And eventually we're going to substitute this volume value into this equation. However, we still need to manipulate this density expression so we can start isolating some of our variables. So what we can do is that what else can mass be? Well, mass is just an expression that is equal to the moles of an object multiplied by its molar mass, which is going to be represented by a capital M divided by volume. If you can see here, we can then replace and or cancel out two of our variables to get here. So we can then rewrite this density expression as such. So our new density expression is going to be, we're just going to write all of this out, is going to be our moles times molar mass over our expression here, which is going to be moles times gas constant times temperature times pressure over 1. And that's, I write pressure over 1 when we have two overlaying fractions, just so we know where that expression is going to go. So we can immediately say right here that our moles are going to get immediately canceled out due to the way this fraction is set up. And then we can say that our final value for our new density expression is going to be, our pressure times our molar mass divided by our gas constant times temperature. This is our new density formula. Okay, so we've kind of not run to a stopping point, but eventually we're going to have to find a way to insert our density into gravity and then use our equation. So what do we do now? So we have kind of we have sort of the basics of our basic equation of fluid statics. However, we need to address another issue, is how temperature is going to change and how internal energy and heat is going to change throughout the system. So I'm going to draw a line here, and then we're going to separate this off and start working on this other side of the problem. So our new expression here is going to be, that we're going to start with, is going to be du, our change in internal energy. Sorry, that's a little bit small for you. It's going to be change in internal energy. It's going to be equal to small amount of heat, which is seen by delta Q here. And that's going to be minus a pressure value multiplied by a change in volume. So this is our normal sort of equation that we can use here to find, we can normally find the change in internal energy. But we want to manipulate this equation around in order to get a better suited equation to start solving for our variables. So what we can immediately say, since due to our adiabatic process, that is zero. Our small amount of heat that's already in the system is gone. So what else can we try to do here? We can, well, our du value is also going to be equal to a constant volume, and that's going to be multiplied by a constant temperature. Or not a constant temperature, a change in temperature. And that is going to be equal to, and then we can manipulate our pressure value here, which is going to be, sorry, we drew that a little too large, which is going to be it's going to be using kind of our ideal gas equation, but we're not going to use moles because that's not going to be important when we're addressing this internal energy, at least not until we plug in our density. So we're going to exclude that value for the time being. So we are going to plug in our gas constant times temperature over volume multiplied by our change in volume. And from here, you can kind of see that we can move some portions of this equation around in order to get our temperature on the left side and our volume staying on the right. And then we can take an integral, which is going to show the change or the sum of the changes of how our process is going to change from this point to here. So let's just get all of our stuff together to where it's supposed to be with our T, with our temperature by our change in temperature, and our volume is already in its proper spot. So we're going to manipulate this in like this. Our constant volume and then to an integral to a new temperature value to a bottom temperature value, or T1, our current temperature, is going to be dt over T. And then over here, we are going to have a new value over here, which is going to be our gas constant, and then to the integral of, which R is going to be our constant, is going to be outside of our integral expression. It is going to be the top portion is going to be going to a new volume, and then we're starting at a current volume, and it's going to be dV over V. And you can tell already, we kind of have a good equation set up in order to get kind of an exponential fraction that we can use to kind of move things around due to the properties of a natural log. So we're going to solve this integral here as such. So we are going to, for the sake of just conserving space in this board, once I'm done with this integral, I'm going to divide this gas constant on each side, and this negative value is going to affect this natural log. And I'm going to show you in a minute. So on this side of the equation, it's going to be constant volume divided by our gas constant multiplied by our natural log of temperature over our initial temperature. And then on the right side of the equation, we're going to have another natural log. Or actually, we're not going to. Actually, yeah, we're going to. Which is going to be our natural log of the initial volume over our new volume. And one thing we can immediately do now is use our properties of natural log and get rid of the natural log on each side. So this new equation is going to be as such. We're going to have our temperature, so that's a little small, a little larger, that our temperature over our initial temperature is going to be to the power of our constant volume over R. And that's going to be equal to our initial volume over our new volume. And from here, we kind of get a little stuck with our equations here. However, we can kind of, since we started with kind of this weird equation up here where we took out our pressure, we're going to actually use another ideal gas law and put our pressure back into the equation in order to find a relationship between our temperature and our pressure. So this volume here, over here, we have a new expression as such. Our new expression, due to this volume, is going to be gas constant times temperature at our initial value times the pressure at initial value divided by the same thing. It's going to be gas constant times temperature for new value times the pressure of the new value. And then technically, if we cancel everything out, we are going to have a new expression as such. We are going to have T1, our initial temperature, over our temperature, excuse me, I keep moving around here, times our pressure over pressure of our initial pressure, or pressure of position 1. And going from here, we can immediately divide this temperature and put it on the left side, and we can then isolate our pressure over here. So what we can do now is say that our temperature over here is going to be, it's going to have an exponent of CV, or constant volume, sorry, that looks like C multiplied by V, our constant volume plus 1, because if we just multiply just this equation by itself, we get that plus 1 up there. And then we're going to have a new expression of pressure, which is just going to be pressure, or new pressure over our pressure at position 1. And now this is where we get stuck once again. So how do we solve this now? What we want to do now is that we want to kind of take this exponent value, because this is going to cause us the most trouble right now. We added to it, and now we need to get rid of it. So what we want to do now, kind of just make a little section right over here. And with that, we want to find a way on how to get rid of that. So let's just write it out. So we have over here we have our constant volume plus our constant volume over our gas constant plus 1. And if we expand that out, it's actually going to be constant volume plus our gas constant over our gas constant. And this has to equal something else. And another way we can sort of simplify this term is taking this in terms of our enthalpy. So we can write out our enthalpy equation. It's going to be capital H, which is our enthalpy, multiplied by our internal energy plus plus a pressure times volume. And this is our enthalpy equation, but we can manipulate this equation to kind of better suit what we want to get out of this. So what we want now is to say that we're just going to rewrite it. So our enthalpy is equal to the internal energy plus our gas constant, R, times temperature. Those two are the exact same equations. And now we want to start taking the derivatives of all of these equations to try to find out what relation we can use in order to get to this, this value up top. So we're going to take the derivative of everything. So it's going to be our change in enthalpy is equal to the change in internal energy plus our gas constant times change in temperature. And if you've noticed, our enthalpy and our change in internal energy can can be expanded out into having this dt value right here. So we can then say that our new expression is now such, is going to be our constant pressure multiplied by a constant temperature, which is our change in temperature, which is dt. And then our change in internal energy is going to be CV, which what we did up here is going to be our constant volume multiplied by dt. And then we just have our gas constant times dt. So since we have all terms having a dt, we can immediately get rid of every single one of those and then just have a new equation as such, which is going to be our constant pressure is equal to our constant volume plus our gas constant. And if we know that, and from here, we can then change this term up top in order to have a new expression, which is going to be our constant pressure is over our gas constant. And then we can swap this value out for this value here. So we're going to have a new value as such. So we're just going to erase that and put our constant pressure over R. And now we can solve for t, or at least a new expression of t, which is going to be as such. Our new value of t, if we first take the reciprocal of our exponent here and put it on our pressure, on our side of the pressures, and then multiply it by our initial temperature, we are going to get a new expression for our new temperature is going to be T, or new temperature is going to be the initial temperature multiplied by our pressure, our new pressure, divided by our pressure in 1, and then it's going to be our, sorry, I kind of wrote that a little wonky, so I'm just going to replace it up top, and so it's going to be P1, and then we're going to have a new expression. We're going to have a new expression of our constant pressure divided by our gas constant. So this is our new T value. And now I believe we are ready to start plugging everything in back into our basic equation of fluid statics and starting to find a function for pressure, which since we have pressure here, we can then use the pressure value we find and plug it into this in order to get a true function that's going to correlate to how our altitude changes with pressure and temperature. So we're going to come over here and draw another line. So starting from here, we are going to plug in our density. We're going to plug in our density value found here and plug it in to this other side of the equation. So what can we do now? So we're going to write this out. So it's going to be EP over our change in, or it's going to be our change in pressure over our change in altitude, which is is going to be equal to, plugging all these things in, it's going to be our negative pressure times molar mass over our gas constant times temperature, and that's going to be times gravity. And what we can do now is substitute this temperature value in for this temperature value. So we're just going to rewrite our temperature over here. So our temperature equals our temperature at 1 at P, our new pressure, times our pressure at R. So now this equation is going to get a little bit more messy, but it's nothing that we can't handle. So what are we going to do now? So we can write our new expression as such. So from here, we can say that our pressure is actually going to cancel with our initial pressure here, but we don't have an exponent for it. So we're going to have to write it kind of in a similar way we did over here with our temperature, with our temperature exponent. So what we can do now is say that our molar mass times gravity over our gas constant times temperature is multiplied by, it's going to be multiplied by P, and it's going to be Cp over R minus 1. That looks a little wonky. So it's going to be pressure times our constant pressure times R minus, sorry, I made a mistake there. It should have been 1 minus our constant pressure over R. And then that is going to be multiplied by our pressure at 1, and multiplied by our, it's going to be multiplied by our constant pressure at R. Excuse me. So from here, we can kind of notice some things here and how we can manipulate the rest of this equation. So we have this change in pressure and our change in altitude. However, we are not going to get this change in altitude expression to match with another altitude variable z. However, we do have some work we can do with our dp value. So what we're going to do now is that we're going to come over here and we're going to divide this value by the whole equation and then bring it over to our left side, and we're going to multiply our change in altitude over here alongside our right side of the equation. So we're going to get a new expression as such. We're going to have a new expression of pressure, which is going to be since we have to flip the expression over, it's going to be our R constant on top multiplied or over our constant pressure minus 1, since we have to flip everything. And that's going to be multiplied by dp. And then over here, we can then bring over our z value, which is going to be our molar mass times gravity over our gas constant times temperature times our pressure at 1 multiplied by our constant pressure over R. And then we are going to have our dz value. And now we kind of have a good setup for our new integral. So our new integral is going to be as such. So we have our altitude value, which is going to be a value of z1 going to a value of z. And then we have our new we have a newer pressure integral over here. It's a little tight, but if you can see it, it's going to be going to a new pressure value, starting at a pressure value of 1. And one thing we can notice is that since this thing is reversible, we can immediately say that at the new pressures, they're going to be kind of the same. So we're going to have a new expression as such. We're going to have a, sorry, there's noise outside. So there's going to be, we're going to have a new pressure value as such. So we're going to have a pressure value of R CP, and then that is going to be equal to a new expression. That's going to be equal to a new expression, which is going to be equal to the way a relationship that this is going to work is that it's also going to be equal to our gas constant over Cp, and then the rest of this equation is going to be our molar mass times gravity over gas constant times temperature. And then what we can do here now is that, actually, one mistake I just caught now is that this temperature value, due to these temperature values, we need to replace that. So this is actually going to be temperature 1 all the way down. So my apologies for that. Now this is our correct equation. Now we have we now have our new expression, which is going to be our pressure at 1 multiplied by our constant pressure R. And that's going to be multiplied by Z minus Z1. So that's our new expression. And now what we want to do now is divide by our pressure at 1 by this entire equation in order to get a new value for our pressure 1. How that's going to happen is that our new pressure, at gas constant times our constant pressure is going to be constant pressure. Say constant pressure, sorry, heat capacity. That's heat capacity. From here, we can then say that this is going to be, P1 is going to be multiplied by 1 minus molar mass of gravity times RT1. And that's going to be multiplied by our Z's, so it's going to be Z minus Z1. So this is our new, and then we can flip the exponent and put it on this side. So this next exponent is going to be placed over here as such. So it's going to be our final pressure is going to be equal to pressure 1 multiplied by 1 minus mg over RT1 times our new Z value to the Cp over R. This is going to be our final pressure equation, and then we can plug this pressure equation into our new temperature equation. So this temperature equation is going to be as such. So our new temperature equation, after plugging everything in, we notice that this pressure 1 value can immediately get canceled out. And we also know that our temperature at 1 can also get canceled out. So we have a new expression as such. It's going to be T is equal to our 1 minus our molar mass times gravity times R, and it's also going to have our sort of pressure value is gone, and our R value is gone, and our temperature value is going to be gone as well. So what are we left with? We are left with this expression over here multiplied by Z minus Z1. And this is our new expression that we have for our and this is our expression that we have for our temperature in regards of our pressure.